All right, class, let's go for it here. Chapter 5, we're going to begin something called rational functions here. So whenever you're talking about a ratio between two things, you're really talking about a ratio. And, all right, really good, thank you. Anything. You could say gas prices and time. That would be a ratio between two things. Gas prices and oil prices. That would be a ratio. Anything that you can sort of put particularly two functions, not so much two numbers. If it's just two numbers like 2 over 3, we consider that a fraction. But once you start putting in variables, an x in there, or x squared, now you're talking about really a function and a ratio between two functions. So now you can go think about things going over time, in a sense. All right. So let's go for it here. So ratio by definition, there it is. It's just two polynomials, one over the other. So we say p over q. P is the top polynomial, q is the bottom polynomial, and we go for it. All right, and just real quickly here, we're going to review just pre-algebra. So if you say 6/8, I know you guys did this here. At least have a good pre-algebra teacher. What the pre-algebra teacher used to make you do is to break down the 6 into its prime numbers. Remember doing that? So 6 had to be 3 times 2. 8 had to be 4 times 2, or 2 times 2 times 2. And then what you would do is you would cross off the ones that are the same on top and bottom, because 2 divided by 2 technically is a 1. Okay, then you guys learned a shortcut. That if you have 6/8, what you do is you just divide the 2. 2 goes into 6, 2 goes into 8, you just divide the 2 out, right? But that's actually a shortcut. Technically what you should be doing is to break it down into numbers that multiply each other, and then cross off the terms that are exactly the same. Okay, does that make sense? That's the long way, that's the more proper way. Why is it the more proper way? Because it has to work that way with algebra. And so when we go to algebra, we have to break this down to its prime numbers. Hey, I think that's why we learned factoring. All of wonderful chapter 4 over there, or chapter 1. All right, so x squared minus 9, does that factor? I think so. Difference of two squares, is that right? X plus 3, x minus 3? Perfect. Yep, x plus 3 is on the bottom. And because the x plus 3, just like on the previous slide, you had the 2 that was a common factor. In this case, you have x plus 3 as common factors. So those will cancel each other out. And you're left with x minus 3 is the reduced and simple form. Okay, we're good. Give you some disclaimers here. Chapter 5 is going to be somewhat dry because we're going to deal with a whole bunch of rules. And we're dealing with fractions, which everybody loves, right? No. I heard the crickets. Okay. And then all the way at the end of chapter 5, then we'll actually get into finally some applications to this stuff. But we're going to just do rules upon rules upon rules upon rules. That's kind of what we're going to do. All right, so first thing is just simplifying this stuff. Factoring, if you know how to do factoring well, you'll be great. Because the tough part here is actually factoring. All right, number 2, all yours. Go for it. All right, again, y squared minus y minus 6. That should factor down into, how about a y times y to get the y squared. And in order to multiply to get negative 6, but add to give you a negative 1, how about a negative 3 and a positive 2? The bottom, again, difference of 2 squares again. So how about x plus 2x minus 2? And the common term gets to be canceled from top and bottom. Leftovers, how about y minus 3 on top, y minus 2 on the bottom, and the question always comes up, Mr. H, why can't I just cancel off the y's? So I'll give you 2 different explanations here. Ready? First explanation is that little slide that we just did before. Whenever you want to cancel anything, you can only cancel things that are multiplication and division. And it comes off this little rule here. Remember, please excuse my dear Aunt Sally? You notice that multiplication and division are happening at the same time? because you have this little situation happening at the same time, you could either be multiplying or you could be dividing, but you can be adding, subtracting. So notice that little minus right here. Minus is holding the y and the 3 together. This minus holding the y and the 2 together. So if you're trying to cancel the y's, you're really trying to cancel off a subtraction, and that's not going to work. Cool. The other way I can sort of, or we can sort of think about it, let's pick a little number for y. I'm going to just choose 10. Okay. So if I put a 10 in here, 10 minus 3. Everybody okay with 7? 10 minus 2. Do these two have anything in common? No. So that little y really is a variable. It's not really a number. And again, you got to look at things that are being multiplied together. Okay, we're good there? So we're canceling factors, but the factors have to be exactly the same. All right. All yours. Go for it. I'll give you a little hint here, something about greatest common factor. Michael, thanks for telling me. I put you in the role, so we're good. All right, let me at least put partially the answer up here. And then a cubed plus 1, that will still factor. Hopefully you remember that that's a sum of 2 cubes. So we're going to factor that somewhere. Kind of looks like this here, a cubed plus b cubed. And so if that's the case, there's the formula, just in case you forgot. I know, it's on the tip of your tongue, I understand. Just go home every single day and look at that formula. All right, the denominator cancels as well. Again, that's, let's see, adding, oh no, the denominator does not factor, sorry. Stays as is because there's no way to multiply to 1 and subtract to 1 or add to 1. Most of you guys are almost done here. Let me go for it here. So the 3 and the 6 reduce. How about 1 and 2? And then that trinomial there. Trinomial is going to reduce itself down because it's the exact same thing top and bottom. So final answer, how about a plus 1 on top and just a 2 on the bottom? All right, any questions on that? There's a few little people staring up at me. Good question. Question is, how come we just don't put a 1/2 in front? This would still be okay if you did it like this. 1/2 a plus 1. That would still be a correct answer. Normally we want to just write it as a quotient. We just want to write it as a single quotient. In this case, you still have multiplication you got to do. So, especially for chapter 5, this would probably be the better answer, just because we want to keep everything in quotients here. Okay, of course, we're just sort of practicing factoring here at this point. So how about this one here? Give you a little clue, something about grouping method or something like that. Okay, I'll do the top. I'll do the numerator here. Remember the grouping method? As you guys are writing down the problem if you need to. We're going to group these in two different parentheses. We're going to put the first pair inside the first parenthesis, the second pair inside the second. It's probably easier just to write out the numerator, simplify that as much as you can first, and then we'll put it all together later. So just the numerator by itself, if I'm working with that, there's my two pairs of parentheses. I can factor out an x out of the first one. I'm left with x plus 4. Factoring out an a out of the second one, leaving you x plus 4. That's kind of cool. Therefore, we get x plus 4 as the factoring out of the binomial factor. That's kind of what it's called, because there's two terms there. Leftovers would be the stuff on the outside, so x plus a. So there's the numerator. All yours to do the denominator by yourself. Alright, let me try the denominator here. So two sets of parentheses, hopefully put x squared plus ax into the first one, 4x plus 4a into the second one. And just checking your work here, the x factors out, x plus a is the leftover. 4 factors out, x plus a again is the leftover, so therefore x plus a times x plus 4. Finally, I can rewrite it here. Here's my factored form of the numerator, factored form of the denominator, and then we sort of see something kind of weird here. I got those factors. They're all the same. X plus a is the same there. So if I have a 1 on top, technically everything is canceled on top, everything is canceled on the bottom. In that case, we just have a 1. A little bit of a sort of tricky sort of kind of problem. If you look at the original problem though, notice you have an x squared, you've got a 4x, ax, and 4a, and 4a. So technically, isn't the numerator the same thing as the denominator, since you're just adding them the same exact ones up, just in a different order? Okay, will that always happen with the grouping method? No, it won't. This is just one of those examples.
If they're always the same like that, they're always equal.
Yeah, if every single term is the same and you're doing the same thing to each term, meaning adding or subtracting, whatever it is, then obviously, yeah, because any number over itself will always equal 1. Okay, so let's take a look at a little bit of a tricky one here. So I got a minus 7 on top, but then on the bottom I have a 7 minus a. And here, kind of two different ways to look at it here, just depending on the way you want to see it. Our preference is always to have the variable in front and the number in the back most of the time. So the numerator I like the fact that it's like that. Denominator, here's my little problem. If I put the a in front and then I put the 7 in the back, notice what happened with the denominator. I had a negative a, now the a has turned into a positive a. I had a positive 7 technically, and that's turned into a negative 7. Isn't this really the opposite of this? Mm-hmm. Okay, how do we show opposite? Yeah, timesing it by negative or a negative 1, however you want to say it. So now, just real quick here, isn't now this the same thing as this? If I were to multiply that negative in, there's my negative a, and then there's my positive 7. Okay, good there? Cool. Alright, when you see that, then you got to see those terms are exactly the same. Those cancel, leaving us with 1 over negative 1, and again, we don't like the negative on the bottom. We can move it up to the top. Also, when you do that, whenever you see a 1 on the bottom, we can just cancel that out. That just sort of goes away. So 1s on the bottom go away. ones on top have to stay because you're saying you have one part of so many. Okay, the shortcut way. Of course I'll give you the shortcut way. Whenever you see this here, a minus 7 and 7 minus a, you know these two are exact opposites already. So my preference is that we just cancel them, but on top what we do is we put a little negative one. So we say to ourselves, we've canceled off an opposite of the term, not so much the term itself. Okay, good there? Then the question comes up, Mr. H, what about addition? Does addition work the same way? Sorry, for number 5, just to finish off, should be a negative 1 on both sides, right? Same exact answer both sides, just done a different way. Alright, so what about addition? So if I have a plus 7 and a 7 plus a, when I cancel these, is there anything that's an opposite to itself or no? I don't think so, huh? Because a plus 7, 7 plus a, doesn't that really mean the same thing? So this is really the same thing as that? At that point, then you can cancel both top and bottom. So this little sort of opposite sort of situation, it's only happening when there's a subtraction symbol. Only when you're switching them around and you have a subtraction there. Any question coming up? No? Okay. Alright, so let's use this here. Let's see if we can use this. All yours for the next problem here. So 7 minus x on top. And a difference of 2 squares on the bottom. Alright, I'm going to start as well here. So on top, I'm going to just leave that exactly the same. Again, you could have changed it up to its opposite, and that's okay. The bottom factors down to x plus 7, x minus 7. And notice what I'm going to do. I'm going to cancel off the opposites, so just leave a little negative 1 on top. When I do that, question comes up, Mr. H, do we ever leave a negative 1 on the bottom? We don't, because remember, we don't like negatives on the bottom. If it's a negative and a difference here, I would always put the negative on top. Cool. So negative on top and x plus 7 on the bottom. That's a perfect way of writing it. That is a true statement. The other way to do it is to put the negative right in front of the fraction, and that is okay too. Okay, so now let's take a look at really evaluating functions here, or thinking about the rational function in function notation here. So here's my definition from the textbook here. I could just make this f of x. I can say this is a function, f of x. That p of x and the q of x, those just means they are polynomials. So I got a polynomial on top, I got a polynomial on the bottom. The only thing that cannot happen with the rational function is that you can't have your denominator equal to 0, right? Remember that from pre-algebra? Remember we can't divide by 0? So that's going to be a little problem for us. We'll talk about it in just a bit here, but let's see how we can just plug in values here. So for 7, x plus 6 on the bottom, x minus 3, I'm sorry, x plus 6 on top, x minus 3 on the bottom. Can you plug in a 0? And what do you get when you plug in a 0? Not going to get a 0, not going to get a 1. A -2 or a -2 might be a good one. Yep. All right. So plugging in a 0 only for the x. So plus 6 on top, -3 on the bottom would give us still a 6 divided by -3. And how about a -2 as our final answer? -6 plugged in. So -6 plus 6 on top, -6 minus 3 on the bottom. So what do I have here? Yeah, 0 on top, -9 on the bottom, right? Hey, is that still okay to have as a fraction? That's okay? Yeah, just 0, right? You can have 0 on top of a fraction. You can't have 0 on the bottom of a fraction. Fractions are pieces of wholes. So if you say 0 over 9, that means you took 0 pieces of pizza that in totality had 9 pieces there. And that makes sense, right? You just didn't eat the pizza.
Why wouldn't you do that with A?
Question? How come we didn't do this for A? Okay.
Like the 0. If you put the 0 on top of -9. I mean,
All right, C and D, all yours. All right, 6 plugged in, and how about a 12 on top and a 3 on the bottom, which makes a 4? All right, and the not so good one here. Plugging in a 3. 3 plus 6 on top, 3 minus 3 on the bottom, so I get 9 over 0. And the answer is? Cool. Can't have 9 pieces of pizza when in totality it has 0. Doesn't make sense. They took 9 and there was no pizza to take the slices from. So therefore, you can say does not exist. All right, this is the online answer to it, right? Just put D and E. Let me just check a little something here in the textbook itself, just to see what they say. So I probably want to say 2, yeah. Undefined? Okay. All right, and this is the online answer. This is when you put D and E because it says does not exist in the textbook here. The answer what they would like is just undefined. It just means that there's no defined number for 9 over 0. It doesn't make mathematical sense. Okay, so let's work with this whole concept of this little 3 right here. That means all the numbers work. I can plug in whatever numbers I like into here, except for a positive 3, particular to this problem. We good? So that means, again, give you a different little name here, something called domain. Domain just means what are the numbers that work. And so we'll go with that. Jump to here. Just a quick definition of domain. There it is just when all the non-zero numbers for Q. So we don't really care about the top piece because the top could be 0, could be 3, could be -12. It doesn't matter. It's the bottom piece that's the problem. So let's jump to something like this here. So for 8, find the domain of this function. And so notice we're not plugging in values anymore. We're looking at the function itself. All right, and F let's see, A and B are pretty easy here because again we don't worry about the top whatsoever. It's the question is, when is x minus 1 going to give me a 0? Probably 1, is that right? If I plug in a positive 1, then we're in trouble because 1 minus 1 is going to give me that 0 in the bottom. So here's my domain. My domain is all the numbers except for 1, or we could say x does not equal 1. So 1.5 works, 10 million works, everything works except for 1.
Rather like that book, that's it.
Yeah, I'm just checking the book as well here. Okay, they put into set notation here. Either or is fine. What they have is they have this, they say the set of all x, and they have this little big bar line come down, which means such that, or based upon the condition of, x does not equal 1. No, those are pretty much almost the same. I mean, if you understand that 1 is the problem, that's what I really want to get
So we
out of
find
you
the
guys.
domain by finding that what's not the domain.
And it's an easier way of saying it, as opposed to saying all real numbers except for x equals 1. This is a really very shorthand to say that's the only problem we have, is the 1. So for B, answer is yep, x cannot equal or does not equal -2. And of course they get tricky. They're not always that easy. Sometimes you do have to factor, sometimes you have to do a little bit of algebra here. So how about x squared minus 1? Does that factor down into an x plus 1, x minus 1? Alright, so what are the numbers that don't work? Yeah, -1 doesn't work here because this will cause a 0 here, and then a positive 1 won't work here because that will cause a 0 here. We know that anything multiplied by 0 will still be a 0. So you can write it two different ways here. You can say it like this: x does not equal -1 comma +1. You can combine them all together in one little sentence and say this right here. It's fine too. You put a little plus minus, just like we did for the quadratic formula. But any one of those two is fine. Okay, and then one more little thing for this section here is something called the difference quotient. And the difference quotient, something that we really look at in calculus. We do a little bit more work in pre-calculus, but this is really the heart of calculus right here. In Math 63, what we really want to do is just to be able to compute with it. That's it. Just to be able to sort of see it for the first time. Can you plug in numbers? That's all. Alright, what in the world is a difference quotient? Difference quotient is this blue line right here. And what it does, it actually measures the slope of the line, notice m over here, from the function at one point to the function at another point. And the interesting thing in calculus here is when you get these points closer and closer and closer and closer together, just give a little tiny bit difference there, you technically get the slope at that particular point, which is kind of cool. Calculus, we say that calculus finally allowed us, the mathematics, to deal with motion, how things go. So when you drive back home in your car today and you look at the speedometer, you're going to thank people that invented calculus, because isn't the slope, isn't the speed of the car technically how fast you're going? It's miles per hour, and so technically it's just the slope of distance that you've gone versus time. Hey, it's a ratio. That's kind of cool. Math is everywhere. Hate it, right? Okay, let's go for it. So our job is just to learn how to just sort of plug in values here. So easy example. Of course, we'll get to the more difficult example. So f of x minus f of a divided by x minus a. So get to know the notation technically. That's kind of what it is here. But before we do that, before we get started, just real quick here, since we're trying to calculate the slope, right? What's the slope of f of x? Just tell me right.
2x minus 7.
That's the
2 over
equation.
1.
Yep, it's 2 over 1, right? The slope is actually 2, so let's see what happens here, okay? So f of x, we're going to plug in f of x, big old quotient bar here, 2x minus 7, subtract, then we have to do f of a. That's okay, we're just going to plug in an a for our variable. So how about 2a minus 7? On the bottom, everything stays the same. Okay, know what happened here. Okay, x minus a on the bottom. Let's simplify as much as we can. That looks like a quotient to me. Let's drop the parentheses first. So how about a 2x minus 7? Then the negative distributes, so how about a minus 2a? Plus 7. Alright, looks like on top the 7's are gone, right? 7's are gone, so 2x minus 2a. On the bottom is x minus a. Hey, this is a pretty good application of this here. Factor out the 2 out, then we're left with x minus a on the bottom. Hey, I think I can cancel those out. And voila. Alright, so usually what happens is question comes up, Mr. H, why do all this work just to get the 2 when I already know the slope was a 2? Because this is a linear equation right here. Remember, a linear equation, this is always the slope. The slope changes when you go to like a quadratic. And so notice right over here, now we got a little bit of work here because I don't know what the slope is. In fact, the slope changes now, right? X squared minus 16, that's a parabola. And the slope will change based upon where you're at on the parabola, just like the speed of your car is going to change, just depending where you're at and how long it took you to get there. So kind of cool. But again, once we were able to determine motion, then we got to do a whole bunch of stuff. So calculus was invented around 1500 or so, in the 1500s. It took us about 300 years for the mathematics of calculus to sort of be worked out and taught and applied, or starting the application process. So the reason why we have so many inventions in the late 1800s, starting 1900s, and so on, is because calculus finally allowed us that possibility to look at, okay, how is anything that moves, how is that going to be affected? Which is kind of cool. Okay, another neat story. You guys ready for that? Way back when, Archimedes, there's a mathematician, he is considered the father of mathematics, or modern mathematics. He was just so close of inventing calculus back in 250 BC. He just did not sort of see this. He didn't see the fact that this equation here would give you the slope. He had this equation here, he had this equation, he was playing around with both of them. 250 BC, the only problem is he didn't have paper 250 BC, so what do? He had like this giant sand pit inside his house. And he used to like do math in a sand pit and did all the calculations and all that stuff. So it kept it in his head. Anybody want to do that? Make a sand pit? Turn in your homework on a sand pit? Okay. Anyways, so when you read mathematics history of mathematics, the question always begs, is what happened. What if the what if of history? What if Archimedes could have invented calculus? What if he just saw the connection between this and this as the slope way back when at 250 BC? The world would have been different. Anyways, let's go for it. So hopefully you tried it while I was telling the stories. So x squared minus 16 should have been in the first parenthesis, a squared minus 16 in the second parenthesis, and the calculation, the way you calculate, is going to be the same, right? You drop the parentheses, you distribute the negative, the constant term is going to fall off, do some factoring. So x plus ax minus a, and then the x minus a cancels. So kind of getting a little more abstract here. So what is this saying? On a parabola, particularly this one, x squared minus 16, let's just say I started when it was 2 seconds later, and I want to test from 2 to 3 seconds. What's my slope from 2 to 3 seconds? And what I can do is I can calculate this right here using slope. So I can just, so at x equals 2, I'm going to go out to x equals 3, or x equals, oh, let's do this here. It's x equals 5 over here. So my slope between the 2 points will be 7. Give you a little visual here. Coming down like this. There's my parabola right here. This is negative 16 because of this guy here. And so let's say we started here, and let's say this was 2, 4. Oh, let's start here. This is 4 because I'll give you a 0. This is x equals 4, and we're going to go up to x equals 5. X equals 5 will be right here. The question is, what's the slope between x equals 4 and x equals 5? All I got to do is plug into this little formula here. X is equal to 4, going all the way to x equals 5 would give me a slope of 9. And so again, driving in the car from minute 4 to minute 5, you can calculate an instantaneous speed right then and there. That's exactly what your car does. Looks at the rotation of your tires, see how that's going. Based upon that, it tells you your speed. Okay, one more just to practice. This one's a little bit different. So notice we have x plus h. Again, same type of, it's still a difference quotient, just set up in a different variation. So let's try this one together. Again, in Math 63, we're just trying to figure out if we can just plug in values, that's it. Alright, so x plus h, that's what we have to plug in. So what I'm going to do right before I plug everything in, I'm going to plug in x plus h into my function, just sort of see what that means. So whenever I have an x, I'm going to replace with x plus h. Does that make sense there? Here's my x here. There's my variable. My variable is multiplying 3, subtracting 9. So if I have x plus h, I am multiplying 3 to this, subtracting 9. In simplest form, I'm going to distribute the 3. And so here's my function for f of x plus h. It's 3x plus 3h minus 9. Right, I'm going to plug that in because now I just figured out what it is, f of x plus h here. So there's my f of x plus h. Subtract the original function, f of x, over just h itself. Alright, give you a little bit of a shortcut here. Do you have to drop the parentheses? Actually, you don't. Because whenever you're subtracting things, can you just kind of get rid of the ones that are exactly the same? Yeah, if you have a 3x over here, you're subtracting 3x, easy enough. That's going to cancel off with this. A negative 9 subtract a negative 9, that's going to cancel off with this. So I'm just left with a 3h on top, divided by h. Can I cancel off the h's? I can, huh? Because isn't h multiplying 3? Right, it's not adding or subtracting. That's what we worry about. Yeah, it's multiplying 3. I can then cancel off the h's.
So what about the negative?
This one right here,
Yeah,
it's
the
technically,
multiplying the
yeah.
negative.
The question is, what about this negative here? It actually just cancels off because it's 3h subtract nothing. All these things got canceled, so there's really nothing else to subtract from the 3h. Okay, real quick here, just to make sure this is correct. What's the slope here? 3, and we get an answer of 3 again. It's just figuring out a way to calculate the slope.
So are they always going to be the same answers?
Only for linear equations. So for 3, if it's a linear equation, like 2x minus 7, the slope here should be the slope here, because that's exactly what you're calculating. X squared minus 16, no, because your slope changes based upon the 2 points. Okay, that was 5.1. Jumping into 5.2. Gonna sort of go quickly here so we can finish. So 5.1, we looked at simplifying rational equations. We just started this one. We're going to look at multiplication or division, but technically we're going to be sort of doing the same thing that we did before. And again, just an example. This is an example of DVDs over time. Looks like a number of copies. Oh, price. Okay, so in economics here, if you make one DVD and you sell one DVD, that's a production cost. If you can figure out a way to make a whole bunch of them and then sell them, your price per DVD should decrease all the time. I mean, that's the whole concept of, especially in the automotive industry. If you can make a whole bunch of cars and sell a whole bunch of cars, as you make more cars, the price of the cars should go down. Turn of the century, that's what Henry Ford is all about. Because at that point, hardly anybody could afford a car. He made a production line where everybody was responsible for one little tiny piece of the car. Right? So once you can get that into a production line, he was cranking out a whole bunch of cars per month in the production. Therefore, it reduced the cost of the car. That's why we drive one. But also be the cars and houses tend to be almost the same price. So literally you had to choose between, do you want to buy a house or do you want to buy a car before the turn of the century. Henry Ford made it so that it's very, very inexpensive. That's what he's known for. All right, this whole thing right here as well. Okay, let's go for it here. So multiplication, a pre-algebra problem first. Hopefully you remember this. It's been a long time from pre-algebra. So if we're going to multiply stuff, we really don't multiply right away because we don't like the big numbers. What we like to do is we like to see if we can reduce first and then we multiply. And then at the end we kind of just check just to make sure we've got everything. So can I reduce anything here? Yeah, how about the 3 and the 27? That will be reduced, right? How about 1 and a 9? How about 4 and 12? 4 and 12, that becomes a 1, that becomes a 3. Cool. And then if you sort of see, oh, hold on, there's a 3 on top still, there's a 9 on the bottom, I can still reduce that. You still reduce it. If you didn't see it, then you would have had a 9 over 3 over here, and then you still would have had to reduce it down to a 1/3. Okay. So eventually it just gets reduced. Okay, so let's go with number 2. Everything's multiplication, so we're going to cancel off numbers, reduce exponents, whatever you need to do. Since we're getting low on time here, I'm going to sort of do the problem with you guys. Keep up with me if you can. Stay ahead of me if you can here. Again, understanding this is the whole concept of that multiplication and division happening at the same time. Okay, let's go for it here. So 4 and 12, how about 1 and 3? 6 and, oh, and there's a 3 on the bottom there, 3 on top, so I just cancel off the 3's there. You could also do 3 times 3 and 6 reduced, that's fine. And you could have done it a slightly different way as well, and that's okay. Okay, reduce the numbers. I only have a 6 on top, and that's it. Some of you guys could have had a 2 and a 3 on top, but eventually you still get a 6. Okay, x to the 4th on top, x squared on the bottom. I can reduce that, leaving us with another x squared on top. And let's see, I got y to the 13 on top, y to the 9 on the bottom. What's going to happen, anybody? You got a y to the 4th, right? There's 4 more on top than on the bottom, so y to the 4th. Hey, notice everything on the bottom just became a 1. If everything becomes a 1, that means you don't have a fraction anymore, you have a full whole number here. So let's multiply everything on top. How about a 6? X squared, y to the 4th. Will that work? Alright, number 3, let's do together, and number 4, I'll let you guys try by yourself here. So I'm trying to multiply these two together. Before I do that, I'm going to see if I can reduce, but before I can reduce, I have to see if I can factor. There's factoring again. So x plus 5 is okay on the top, but x squared minus 25 factors down into x plus 5, x minus 5. Okay, x minus 5 on top, yep. And let's see, I need two numbers multiplied to 25, add to negative 10. I'll go with x minus 5 and another x minus 5. So negative 5 times negative 5 would give us that. Okay, and cancel off whatever you like. Top and bottom as long as they're the same. Alright, got x plus 5 here, x plus 5 here, gone. X minus 5 gone. So hopefully you guys all have two x minus 5 factors. Two different ways to write it. Whichever way you like here, you can keep them separate if you like. X minus 5. Alright, you can also combine them, and this is, again, same exact problem. You could say x minus 5 to the 2nd. So you have to just write it down once. You're saying there's two of those. Okay, number 4, all yours. Go for it. Can you go beginning to end? Alright, I'm going to start it as well here, just because we might be running out of time here. So factored. Here's all my factoring done. So look up just to make sure we factor down correctly here before we start canceling. And factoring is the tough part here. If you can do the factoring, you'll be okay. Alright, and now canceling. Let's see, I guess the 3's will go away first. 3's are gone. Y minus 4 and a y minus 4, those are the same. Y plus 2 all the way at the end. Those go away. So then on top, don't forget this little y over here. I got to factor out still. You got a y times y minus 1. On the bottom, I just have a y plus 1. And again, can't reduce that anymore. There are no factors that are exactly the same. Okay. That's multiplication. Let's jump to division. And if I'm going a little bit too fast, if you want to see any of the slides after class, I'll be more than happy to show them, okay? Just tell me. Okay, let's jump to division. Again, a pre-algebra example first here. And anybody remember how do we divide fractions?
With 27/10.
Cool, yep. We keep the first fraction exactly the same. We change the operation to a multiplication, and we understand that if you do that, we have to take, remember with addition and subtraction, we take its opposite, right? But with multiplication and division, we take its reciprocal, because that sort of undoes the operation itself. And at that point, then we start reducing, simplifying, whatever needs to get done here. So 5 and 10 make a 1 and a 2. But a 9 and 27, 1 and 3, and voila, 3 halves is a reduced form. Keep it as an improper fraction is fine. Alright, 6. Because I'm running low on time here, we'll do it together. Those of you, of course, that printed out your matched problems, so easy, right? Because you don't have to write down the whole problem all over again. So let's go for it here. I'm going to write it down so it's a multiplication problem now here. Again, taking the reciprocal of the fraction that's after the division sign that we changed. And reducing stuff here. So 9 and 3 make 3 and 1. 4 and 8 make 1 and 2. X to the 4th on top. X squared on the bottom means another x squared on top. And y cubed, y to the 5th means y squared on top. And again, all this bottom reduced and canceled completely. Kind of careful here. You got a little coefficient of 2 here and also a coefficient of 3. So you got these guys. So multiplying together gives you a 6. Then we have x squared, y squared. So yeah, you want to, in this sense, at the end, multiply all the numbers together. At least the coefficients here. Alright. Jumping to 7 here. Looks like 5 minutes left and 1, 2, 3, 4. 4 problems in 5 minutes here. Let's see if we can do that. Alright, I'm going to start it as well. But you try to stay ahead of me if you like. Factoring out an x, that looks like a y squared out of this one here, leaving us with x minus y. In our denominator, it's the difference of 2 squares. Put a multiplication symbol. I'm going to switch the 2. And normally what students do is when they switch the 2, they start at the same time factoring as well. So it sort of does 2 steps at once. So this one is actually a perfect square trinomial. So, and then on top, this is actually a difference of 2, oh sorry, sum of 2 cubes. So again, going back to sum of 2 cubes formula, to sort of go back and look that up again if you need to here. Sum of 2 cubes, even though we did see something like that earlier. And then the denominator, which goes on top over here, this is actually a perfect square trinomial, because you have perfect squares at the ends. And if you double it, multiply these and double it, you get 2xy. So this would be x plus y, another x plus y. And again, the factoring is the problem area here. Alright, once we're factored, good to go. X minus y, x minus y, x plus y, another x plus y, And left with, how about y squared, which is the only thing left on top. And then this whole entire trinomial here is on the bottom. Alright, and next one. How about if we have multiplication and division at the same time? So the only one that really needs to be taken a reciprocal of or flipped is this last one at the end. So you only take the reciprocal of the number in back of the operation you are changing. So I'm going to start factoring things down here. Give you guys a little bit of a head start. So how about an a plus 4, a minus 1, a minus 4 on the bottom, a plus 3 on top of the next one here. Two numbers multiplied to 3, add to negative 4. Negative 1, negative 3, I guess. So that would become a minus 1, a minus 3. Alright, so the a plus 1 went to the bottom from the top. Then I need two numbers multiplied to negative 3, add to negative 2. Perfect, yep. Positive 1, negative 3. Doesn't matter which one goes first, so negative 3, positive 1 is going to work. And again, at that point, then we are canceling like terms, top to bottom. A minus 1, gone. A minus 3, gone. A plus 1 is gone. Getting to your answer here. On this problem here, in the matched problems for number 9, it kind of doesn't make sense because there's an equal sign in the middle of everything here. So I don't know if they corrected it, but that should have been actually a plus sign. So it should say xa plus 2x plus ya plus 2y. So if we can fix that first before we start the problem. Alright, so as we start this here, again the plus sign is here, not an equal sign. And so again this is factoring by grouping, and we have to do each an individual numerator denominator by itself into its factored form. That's what makes this a little bit tough. So the first two terms go inside the first parenthesis. The last two terms go inside the second parenthesis with sign. So make sure you got a minus ya here. Factoring out the x in the first parenthesis, factoring a negative y the second, leaves us with the factored form, which is a plus b times x minus y. Alright, taking the denominator now, and then doing the exact same thing here, putting the first two terms inside a one parenthesis, last two terms in another. Factoring out the x leaves us with a plus 2. Factoring out the y leaves us with a plus 2. Factoring out the a plus 2 then leaves us with x plus y. So there's my first fraction. I have factored this one. Again, you can can try this right here. Try to factor that one by yourself before I do it. Alright, and the second fraction here, numerator, using grouping method, factoring out the x out of the first parenthesis, the y out of the second, and eventually get a plus 2 times y, a plus 2 times x plus y. The denominator, factoring out the x, a plus b, factoring out the y, a plus b, and factored form of the denominator with a plus b times x plus y. Now putting this all together. So first fraction, denominator of the first fraction, second fraction, denominator of the second fraction, and now we get to cancel stuff off. So notice the factoring is the complicated aspect here. Alright, with that, just canceling things that are the same top and bottom, or the same factors top and bottom here. So a plus 2 is gone, x plus y is gone, a plus b is gone. Hey! Oh, there it is. X minus y is the only term that's left on top. X plus y is the only term left on the bottom. Therefore, this is the simplified version of that big, humongous multiplication of the two fractions. Alright, and the last problem is this right here. How do we deal with sometimes you have one that's not a fraction, the other one is a fraction. In this case, we just make both of them to be fractions, just like we did in pre-algebra with numbers. And we have to factor, of course. So 5x squared minus 45, factoring out the 5 first as a greatest common factor. Everything else remains the same on the bottom of the first fraction. The 3 remains the same on the top of the second fraction. But we can factor out a 5 out of the denominator of our second fraction. And it still can be factored out some more. How about the numerator of our first fraction still goes to x plus 3x minus 3? And now we can see the 5's can be cancelled, x minus 3's can be cancelled, and eventually we'll get an answer of just 3 times x plus 3. And notice, do we just have 1's on the bottom of the fraction? And since there's just 1's on the bottom of the fraction, we don't really need that because now we have a whole piece. Alright, and this is the end of 5.2.